Okay.
Okay, so welcome, Bal, and thanks for agreeing to give this lecture. You are an old friend of Dias, and you've worked with my predecessors here, especially Lachlan or Rafferty, and a frequent visitor from, I think, from even the 60s. So it's a great pleasure to have you and the possibility to record this talk. Thanks again, and welcome to everybody. So whenever you're ready, I'll take over.
Yeah, okay.
Causality in quantum field. You need no introduction to this audience.
No. Okay. Let me start. Okay. This is a problem which was posed by how do I screen? Screen is not changing.
Arthur explained to you that control shift or shift return or something does it.
Shift return. No, it is not changing. It is frozen. The screen is frozen. Let me see. Hello?
Yeah.
I have to change it manually. Okay, fine.
Okay.
Okay. So this is a problem which was posed by Rafael Sorkin quite a long time ago in 1993. Okay? And it has been under discussion more on and off by people. Okay? And what I am reporting here is a lot of discussion with Francisco Calderon and Andres Reyes Lega in Bogota, Parameswaran Nair, Sasha Pinzul in Brasilia, okay? And Sachin in Coimbatore, okay? Not in Bengaluru, Sachin Vaidya. Okay? So what Rafael proposed in 1990.
I think you also your interest in it started with some of our postdocs here at Dias. Is that correct?
Sorry?
So your interest in this problem also started with some of our postdocs like Ian Jubb and
yes. Yeah, two people here in Dias also stimulated me to look at the problem, and then we started discussing. That is true. Okay? Ian and
Leron.
Leron,
I believe, and
Leron, I think, is not there, right?
No, he is no longer with us, but he was a postdoc here at the time.
Yeah. Okay. So
and I think Graham as well was.
So we started on this problem, okay, looking at this problem, and the experiment proposed by Rafael is shown here schematically here. Okay? So first you have the standard Bob, Alice and Bob, okay, at times t less than some t1, okay, and you have a state rho which is shared by both of them, and they know what it is. Okay? Then in region 1, okay, Alice does a projective measurement. Okay, so she may or may not, I should say, she may or may not measure an observable A hat at time t1. Okay? And then if she does a measurement, let us say it is a projective measurement. Okay? So this experiment is going on in the region O1. Okay? Then in region O2, okay, some other operator B hat is measured at time t2 larger than t1. Okay? So O2 is this region. And finally, in region 3, okay, which is space-like separated as regards region O1, O3 measure, looks at the expectation value of some observable. Okay. What Rafael found was that in the standard scheme of measurement theory, the expectation value of observables in O3 depends upon whether or not Alice has done a measurement. Okay. And notice that O3 is space-like relative to O1. Okay, so how can this be? This is the problem, and I'll show you how it happens. Okay, so notice also that the region O2 is not all space-like relative to O3. Okay, so there is some portion of O2 can be say tide slice. Okay, some Cauchy surface, but it could also be some boundary region. But some portion of O2 is time-like relative to O3. Okay. So let us see what happens. After Alice's action, rho, the state rho, which is the initial state at times t less than t1, becomes some state sigma, which is some projection operators pi of O1, rho pi of O1, where the projectors sum to 1. Okay? So the Pi of O1 are projectors localized in O1, and you have this equation here. Okay? Then in region 2, okay, the measurement of O2 changes sigma. This state we are getting after Alice, she does the measurement or does not do the measurement. It could be that the Pi is just 1. Okay, so it is just one term here. Okay? Then after measurement in region 2, O2, sigma is changed to some Pj of O2, Pi of O1, rho, Pi of O1, Pj of O2, and the corresponding state is tau. Okay? So the Pj of O2 are projectors on spacious slice 2. Okay? And of course, Pj of O2 also sum to 1. Now look at the expectation value of an observable, C of O3, localized in region 3. Okay? The mean value of an observable, tau in region 3, tau of C of O3 is trace of C of O3, Pg of O2, Pi of O1, rho, Pi of O1, Pg of O2. But this expression is not is sensitive to what is Pi of O1. Okay, you can see why. The reason is that the Pg of O2 does not, this projectors need not commute to CO, will not in general commute to CO of O3. If they did, then I can pull it through CO of O3, sum it on J, okay? Then it goes away, the PJs go away. Then since O1 is space-like related to O3, that also goes away by causality. So we are, the expectation value does not depend upon what is happening with Alice in time t1.
Sorry, Bao, can I ask a question?
Sure.
You're summing over J.
Yes.
Are you using the summation convention?
Yes.
Okay.
That is okay. So this is what this is rough. Basically, I see that Ian is here. So Ian is here. He can also comment. Okay? So this result has been with us for a very long time, okay? Since 1993. Okay? And in 2020, Bostelman et al. There were also papers by Fay and collaborators, okay? Fay Dowker and also Ian and Leron. Okay? There are others also. So the particular formulation, which at least we found satisfactory, comes from Bostelman et al. Okay? And it is using local quantum physics. Okay? I would say that the ideas which are underlying this work, seems to me at least, is to go back to Stueckelberg already. Then certainly Bogoliubov is his formulation of scattering theory and renormalization theory, and Epstein and Glaser, many other people like that. So calculations which were done much before related to causality, based on causality, seems to go into this result. Okay? So let me go and present to you our interpretation. Okay? Okay? First statement is that projection operators for local regions do not exist in local quantum physics. Okay? So this projection of, so to say that O1 is a region and one does a measurement on O1 and there are projectors which are, say, orthogonal to region O3, that is not possible. I'll come back to this in local quantum physics. If it is space-time region, this is already true in quantum mechanics. So I'll come back to that in a minute. Okay. So
I would think a lot of people would say that there are projections localized to regions, projectors that commute with operators outside or space-like to that region. The standard von Neumann algebra picture, they're just not a finite rank.
I said orthogonal. There are no finite rank projectors in. Yeah. Okay.
So, but there are infinite rank.
They are not
projectors.
They are not useful in the present context. So we need. I want. And there is also Hager-Fels result, which I will recall for you. Okay. So the kind of projectors we need do not exist. Namely, we have to separate the events which are happening in O1 and O3 and the corresponding projectors. Okay. For example, Bond's interpretation of quantum mechanics, the kind of projectors which go into that, okay, does not exist in local quantum physics. Okay. So we have to do something else. So the clue here seems to be that we should talk about local couplings. I'll come back to that again. I think this is quite important. So we look at a disturbance in O2. Okay, instead of saying that O2 is making a measurement, we imagine a disturbance, some Hamiltonian density coupling some test function localized in O2 and some two quantum fields phi and chi. Okay, where the support of alpha is O2. Okay, and phi and chi are quantum fields. Okay, so then how does it go? Okay, then it is rather quick to see what is happening. So first, let us look at the causal past of O3. Okay, so drawn here in the picture. Okay, here schematically drawn the causal past of O3, J minus of O3, and it is intersecting region O2 in some region. Okay, and I also look at the causal future of O1, and it is intersecting O2 in some region. Okay, so the crucial point is that the causal past of O3 and causal future of O1 may or may not intersect in region 2. Okay? In case they intersect in region 2, then it is not O1 and O3 are not spacelike. Okay? Remember that if they intersect, okay, the statement that something is to the future and future pointing and time-like is a transitive relationship. So if they intersect, O1 and O3 will not be space-like. So then there is no problem to solve because they are not space-like. However, if they don't intersect, okay, then they are space-like. The causal past of O3 and causal future of O1 do not intersect. So they are space-like. Okay? But then if you do causal perturbation theory, for example, write the formula using time ordered products for the interaction I wrote down and see what is happening in O3. You see quickly that there is no influence of J plus of O1, the region which is time-like to O1 on what is being measured here. Okay, all that influences the expectation value in O3 are the interactions which are taking place in J minus of O3, and if that is space-like related to J plus of O1, you find no influence at all on what happens in O1. Okay? So if you just use time-ordered perturbation theory, which is underlying, let us say, much of the calculations of Bogoliubov, I think Bogoliubov, Shirkov, and others, okay? And also, I should say, Epstein and Glaser, you find immediately that the causality problem has disappeared. Okay? So what, as I said here, is what matters are the intersections. Saying again, the causal future of O1 intersecting with O2 and the causal past of O3 intersecting with O2. Okay? And the mean values of O3 are affected by only the causal past of O3, okay, which is in O2. Okay? This O2 O3, and so this interaction is what this integral is what is affecting what is happening in O3. Okay? And if these two are not disjoint, then O1 and O3 are not space-like, and there is nothing to discuss. Okay? So while if they are space-like, okay, then only this term affects what is happening in O3. Okay? So there is no causality violation. So this is a simple presentation of how the problem gets resolved. And I think the important thing is that we are remembering already the old dictum or guess of Faraday that local fields are essential to cover causality. Okay? So the moment you write quantum field theory, this kind of problem apparently will not arise. Okay?
Sorry, I just also wanted to make a little point there about the consistency of this with Rafael's stuff, because the stuff that Chris Fuster, Henning, and Maximilian had done that you're talking about, this local couplings stuff, that once you trace out the probe quantum field that, or whatever it is that you're doing, you end up with an update rule on the state for whatever's happening in that second region. And as you said, you don't get any causality violation. And so therefore, from Rafael's stuff, then they're consistent in the sense that what's just happened in O2 cannot be an ideal measurement of the operator O2, because if you had measured it ideally, then you would have a causality violation. So this update rule using local couplings, which is a nice model, is consistent with what Rafael had said. In that
except that local, my claim, from what I understand, is that this standard thing about ideal measurements with projection operators do not exist in quantum field theory. Okay?
Right. Well, that's not the case. You can have the Luder's projection postulate with projectors that are localizable, and you can write that down, and that's something that can be done in the full-on AQFT language. So you can formulate Rafael's problem in that language, and then AQFT people would say, right, well, we need to go and do something about that. And this is exactly why Chris and Henning came along and thought about this probe, this locally coupled probe picture in the first place, because Rafael's problem that he highlighted is a problem in QFT proper.
What are these projectors? Okay, let me, I think I'm not agreeing with you, because I don't know what these projectors are in quantum field theory. Okay? There is, we need a space, presumably we need space-time projectors, okay? And they don't exist. Projectors in the sense of being orthogonal. Okay? Such projectors do not exist, okay, because of a simple argument due to Hagerfeld, which I will present in a minute. Okay? So I don't know.
But perhaps we can come back to the discussion part of it Ian later.
Okay. I don't know what the projectors are.
Okay.
I don't know how to write them. In quantum mechanics, yes, but not in. Okay, I'll come back to that. Okay. So if you put non-local couplings like this, okay, for example, a coupling like this in space in region 2, I should have written x1 here. Imagine that it is belonging to the region 2, not 1. Okay? And suppose it is actually space-like relative to the original O1, but the integration on x2 and x3 still runs over regions which are time-like related to O1, then the argument fails. So there is causality violation. Okay? So non-local couplings like this do cause causality violations. Okay? So in general, we end up by going back to the kind of condition that Bogoliubov was using, that the Hamiltonian densities have to be local operators. Okay? So if you have such a condition, okay, then there is no faster than light signaling. Okay? Incidentally, this condition also solves an old problem due to Fermi. Okay? What is a Fermi problem? Okay? Here is a Fermi problem. Okay? You have two atoms. Okay? I think Andres, who is in the audience, he has read the paper, which I have not read. Okay? So you have two atoms. One is localized in a region alpha, the other is localized in a region beta, and they are a distance r apart. Okay? Alpha is in a ground state, okay, and beta is in some excited state. And at time 0, the quantum state is psi at time 0. Some quantum state is alpha localized here. For a state for the atom B, beta state is beta, and the photon is in the ground state, let us say 0 of gamma. Okay? Where gamma 0 gamma is the Fock space vacuum of the photon. Okay? Let us say that beta decays to ground state emitting a photon. Okay? Then causality requires that alpha, the state alpha on the left, is not disturbed by the photon, but times t less than r over c. Okay? Okay? So what does it mean? Okay? That's the naive formulation of causality. Let us see what it means. Let's consider the projection operator, which I have written down here, okay, which corresponds to alpha being in the original state and unity and unity. So we don't really care about what the other two things can be anywhere. Then if you look at Q1 minus P, Q equal to 1 minus P is a projection operator for finding the left top atom in any state but alpha at time 0. Okay? So this is the projection operator which will whose expectation values will tell you whether the state of alpha has changed. So by causality, if I evolve the expectation value of this projection operator evolved for a time exponential IHT, exponential minus IHT, in the state psi 0 should vanish for t less than r over c, where c is the speed of light. Okay? So this would be the formulation of causality in, let us say, in the standard formulation. Okay? But this leads immediately to a surprise. This is correct. Either the left atom will never get excited, or it will get instantaneously excited, violating causality. Okay? Okay? This is the surprise. Why? It's quite easy to prove. Okay? The proof is Q is a projection operator, so Q squared equal to Q. So we know that this expectation value is 0, okay, for t less than r over c. So this is simply the this Q squared. So this is simply saying that the norm of the state Q exponential minus IHT acting on psi 0 is 0 for t less than r over c. Okay? Okay. Now, this equation implies, okay, that if I expand this expression in energy eigenstates, okay, I get the fact that I put a complete set of states here. I assume everything is discrete. I can make it more complicated. This says that this is equal to exponential minus IET times this expression is 0 where t less than r over c. Okay? So the problem is this expression here, and the fact that the energy, the Hamiltonian, is bounded below. Okay, so let us say it is non-negative. Then, since we have H non-negative for E is positive. Okay, so let me first consider E strictly positive. Then, if I imagine T as a continued to the complex plane, tau is T plus Im tau. Im tau is negative. You see that this expression, okay, for tau is my complex variable time. This expression which I am discussing, okay, becomes, in terms of these variables, exponential minus IET plus IE times imaginary part of tau. Okay, but this is holomorphic. This expression is holomorphic in the lower half plane of tau. So if the imaginary part of tau is negative, okay, this expression is holomorphic in the lower half plane, and we are telling that on the real axis it is vanishing for t less than r over c. Okay, so by and some continuity assumptions, one knows by, I think, Short's reflection principle, that this means that this is identically 0 by analytic continuation. Okay, so we have ended up by saying that the expression I started from, this expression I started from, or this expression I started from, is identically 0 if you give me this condition, okay, then this expression simply vanishes, in fact, for all time t. Okay? The only exception in this calculation is I omitted the case of energy being 0. Okay, but this object here is entirely time independent. Okay? So the transition has to be instantaneous. If assuming discrete spectrum, okay, this transition must be instantaneous. Okay? But the whole thing is absurd. Okay? So what has gone wrong? Okay? So this is the Fermi problem, and again, this is solved very late by Buchholz. There is a paper by Buchholz and Ingvarsson. But anyway, we can see what is happening. Okay? There are no localized states or localized projectors. Okay? This is the first statement I make. Okay? Why? For suppose there were a state E delta. So when I said delta is a bounded space-time region, is such a projector. We want to here to be localized in space-time. So the two atoms are sitting apart in space-time. So we would like a projection operator which is localized in a bounded space-time region, delta, E delta, and it is such a projector. Then E delta on vacuum is a localized state. If such a E delta existed, will be a localized state with 0 being the vacuum, for example. Okay? Now, for sufficiently large t, larger than some capital T, the intersection of delta and this translates by time larger than t is null. Okay.
Sorry, Bal, what did you mean by a localized state?
This object will be orthogonal to any E delta where the region, that's what I'm going to say now. Okay. This second line will answer your question. Okay. So, a localized state in the sense of, let us say, Bond's interpretation of quantum mechanics. So, if delta and delta plus some t larger than t, okay, their intersection is 0. Okay, we would like E delta and E delta plus t on the vacuum is 0. Okay. Okay. So we would like
is that like if you had two projectors for two space-like regions or something?
Spatial slices. In quantum mechanics, this will correspond to, say, on a time slice, you take two spatial regions which are not intersecting. So you write down the projection operators in these regions, and they are orthogonal. In that sense.
Sorry,
so,
two segments of the real line or something that are disjoint.
Which are not overlapping. Yes. Okay, this is what is used in Bond's interpretation of quantum mechanics. Okay? The probability of finding something somewhere is given by psi of x whole squared. Okay, is based on this fact. Okay? So if this is the case, suppose this is the case, this means that this expression is 0 for t larger than capital T. Okay, where capital T is where the two regions become non-intersecting. Okay? So the Hagerfeld argument is this, that if you give me this, okay, so we start from the existence of localized projectors, okay, in space-time, okay, then they exist, that leads to this expression for energy Hamiltonian bounded below. But then by the previous argument I gave you by of analytic continuation, you can again continue this expression into the imaginary plane. Okay. So since a Hamiltonian,
can you go back to the previous slide? I was just trying to follow the argument closely enough. Oh no, the slide after that. I mean, going forward, so probably slide 13.
Slide 13. Okay.
Yeah. You in the second last equation you've got there, you've evolved the projector E delta, say, forward in time.
Yeah.
And you're asking, and you're saying that this is 0 for t greater than some capital T?
Yeah, because the delta is a bounded space-time region.
Yeah.
And I'm translating it in time.
I would, my understanding of what that would mean is that you're expanding the projector. It's getting, its support, in a sense, is getting larger because.
No, he's using translation, trying to use translation in time.
But this expression that you've written is how you evolve operators in time, and their support will spread just like the support of a classical function when you evolve it in a relativistic way using, whatever Klein-Gordon equation or Dirac equation. If you have a function which has some compact spatial support, and then, or you have Cauchy data with compact spatial support, and then you evolve it, the support grows, expands out, at the speed of light or whatever your limit is in your relativistic system, then the same would be true for a projector or just any operator. So I would imagine this is not going to be 0. There's not an obvious, you can't evolve it. You can't just evolve it in time and then imagine that it would have no overlap with something back in time. That's not how operators algebras work in quantum field theory. There's the time slice property that operator algebras in different time slices are the same.
You may let me say I'm you may be okay, sorry, let me say that this is I agree with you. Okay, I understand. So the statement of Hagerfeld is that if you assume this naive property, you get into contradiction. Okay, so he abandons this hypothesis, and I agree with you. I mean, I was also worrying about this. For example, in quantum, this argument also applies in quantum mechanics. So what is going wrong is exactly what you are saying. Okay? So we are in agreement. Okay? There is no problem. Okay? And in fact, I am not going to use this. Okay? So I'm going to say that this is wrong. Okay? This is wrong because of the fact that evolution will mix up things, okay, in a different way. So if you try to write projection operators in space-time regions, even in quantum mechanics, understanding by that projection operators in disjoint regions are orthogonal, then there will be trouble. Okay? That is all I am saying, which is compatible with what you are saying. Okay? So that's okay, I think. I think so. Yeah. I am not. I think we are not in contradiction. Yeah. Okay. So, so he arrives at the fact that you get absurd results. Okay. So Hagenfeld says, okay, so again by analyticity argument, this expression vanishes for all t. Okay. Again, by continuing it in the complex plane for imaginary part of tau positive, it vanishes for all t. Okay. So for t equal to 0, you get this. Okay. Then from here, you infer that E delta annihilates the vacuum. Okay. Similarly, you will conclude that E delta annihilates any state, at least any state, any vector state, which let's say which is in the domain of the Hamiltonian or finite energy. It will annihilate it by the same argument. So you would say that E delta is 0. Okay. That is absurd, which is wrong. Okay. So this is the argument of Hagenfeld that such projection operators do not exist. Okay. But again, we can model the transition of the right atom at time 0 by an interaction. Okay, some interaction like this. For example, the current, electromagnetic current of the right atom couples to electromagnetic vector potential mu with some test function beta, where the supporter beta is the right atom. Okay? So the causal past of the location of the left atom for time less than ROC does not intersect this support of this HI. Okay? So again, by the same argument I gave you earlier, okay? Argument going back to people like Stueckelberg, Bogoliubov, Epstein and Glaser, whoever, okay? You find that the left atom will not make a transition for time less than ROC. Okay? So the Fermi problem is again resolved by using quantum field theory in a fairly simple way. So this is, I wanted to bring to your attention these two results. Okay? And let me make, in this context, some final observations, okay? Which I will continue in my stuff on addendum. Okay? So let me make final observations. One thing we found out in the course of this discussion, okay, was that it is not possible to determine a state omega on a local algebra A, okay, in a bounded spacetime region O without an external reference algebra R. Okay. It is not possible. Even in quantum mechanics, if you do not have a reference algebra or reference, which I can call apparatus, okay, if you don't have it, one cannot make appropriate measurements on to determine a state or a local algebra. Okay. What do I mean by that? Okay. This already, as I say, partially the case in quantum mechanics. So a state in quantum mechanics is given by a density matrix rho. Okay. So the expectation value of an observable A in this state is given by tracer rho A. Okay. Now, knowing the algebra A means, okay, for example, defining it by generators A1, A2 up to AN, with, for example, by appropriate relations. The relations can be this kind of equation. AI times AJ is some combination of the other generators or something like this. Okay? So we are given the algebra abstractly. Okay? All that we know are the algebraic relationships. Okay? Okay? But if you are just given the algebraic relationships, okay, and if you take any unitary in the algebra and make a unitary transformation, okay, which I call, so the conjugate of AI is I call U AI U inverse, AI of U. They fulfill exactly the same relations. Okay? So we can identify the, if you say measure A1, okay, I can do that only up to a unitary transformation of A1. So all that I know is rho times trace of rho times AI of U. Okay, that's all I can measure. Okay? But this is the same as the conjugate of rho by U, okay, by the unitary with AI. So we can determine the state only up to unitary transformations. So we can at best measure its eigenvalues, or let us say its characteristic polynomial, like determinant of rho minus lambda. Okay? And we cannot separate omega rho from omega rho of U. Where omega rho U, I mean the state obtained. Did I write it? Okay. Where omega rho U, okay, is obtained by, yeah, this state here, okay, U rho U inverse is omega rho U, and that is we can all that here it is. The definition is right here. Omega rho U is defined by I say that on A it is omega rho U times A U inverse. Okay, so we cannot determine a state by intrinsic measurements of the observables. We need an external apparatus. Now, I'll come back to this. Okay, in what happens in quantum field theory is much worse. Okay? Okay. This is due to the fact, at least in local, these are local measurements. The algebra A of O on a localized spacetime region, finite spacetime region O, is known to be of a type 3-1 von Neumann algebra. Okay? We don't need the details of this algebra, but what we know is that if you give me two density matrices rho and sigma, okay. By the way, rho and sigma are not in this AO, but doesn't matter. It's some finite dimensional trace class operator rho and sigma normalized to appropriately, so that trace is 1. Then the theorem, a theorem says that we can find a U in the algebra AO such that the orbital rho under U, okay, is arbitrarily close to the given sigma here. There is U rho U inverse on A minus trace of sigma of A traced is arbitrarily small. Okay? It cannot be 0, but it can be made arbitrarily small. Okay, so it's dense. The orbit is dense. The space of all states. Okay, this is a theorem due to Kohn and Stormer. Okay, and it is characteristic of this type 3-1. But we already saw in quantum mechanics that this problem exists. Okay? So there is no way to determine any state by internal measurements. Okay? So we need a reference system, R. Okay? And the reference system, I don't, the reference system is again a quantum system. Okay? So it will have the same kind of problem. If the whole system is quantum, the same kind of problems, unless for some reason the algebra of operators associated to R becomes commutative. No, how does the commutative algebra emerge from in the measurement apparatus? Although if that is not the case, we have again the same problem, and so it will be an unending unending problem going on repeating. Okay?
Sorry, so, well, epsilon is a dimensionful quantity. It's not a pure number in general.
Epsilon can be a dimensionful. Well,
so it must be referred to some. I mean, if the operators A and the algebra are have some characteristic dimensions, then epsilon will have the dimension of that operator.
You may have to divide it by some dimension full constant, okay, to get some. So epsilon modded by some
dimensionful constant. So there's some reference. The point is that there's some reference length scale for which you can reduce it to with regard to that.
Yeah, I think that's correct. But you can make epsilon arbitrarily small. The orbit is dense. That is a sure statement. Okay? So the issue is, what is the description of R? Okay? So let me say, before I go to the next slide, okay? What are the proposals which exist in the literature? Okay? There is a paper, okay, which I see Giorgio here, And Giorgio and his colleague, whose name I will give later, had already proposed in a paper in 1994, from what we saw, that the he was actually talking about non-separable Hilbert spaces. But let me formulate, and he was saying that the apparatus, okay, is an unstable system which can undergo phase transitions. So the different phases into which the apparatus can go as a first order phase transition, the labels of those different phases are the observables which are characterizing R. Okay? So this is one way of formulating it. And subsequently, we discovered a paper by Arthur Weitman, who who I don't know who did it first, okay, says that if you take the superselection sectors of the algebra, then imagine operators which label the superselection sectors. Okay? So you put some set of operators which label one, label the other, and so forth. Okay? And since they will since they are labels, they can be simultaneously diagonalized, so they form a commutative algebra. And by construction, the observables will not change them. Okay? Because the observables are not in this labels that you're talking about. And the prescription of the conjecture or statement of both Giorgio and of Weitman is that these superselection sectors, which can be created, for example, by phase transitions, are the ones which cause this emergence of a commutative algebra. Okay? There are explicit models, okay, which suggest, I mean, there are alternate models, okay, which may, in this I am not sure, but may be actually similar to this. First, what I know is by Klaus Hepp long ago, okay, and so that gives an explicit model where a local disturbance creates what they call, I think, operators at infinity, something like that, a construction due to Lanford and Ruel. Okay, so he uses that construction. So there are alternate models which may be possible to formulate in this language. Okay? So what I want to now to do, okay, so there is a problem. Okay, so what is being measured by the apparatus is a commutative algebra. So we are faced with the problem of how does it extend to the full algebra. Okay? So I want to look at that problem. Okay, so let me go on here. Okay, so I want to state a problem, okay, which more on measurements. Okay, so I am accepting the accepting that what is measured experimentally is a commutative algebra. By the way, this is also very consistent with what Niels Bohr was emphasizing already in his earliest papers. Our masters in quantum physics, they were emphasizing from the earliest days. But at that time, it was not very clear how this commutative algebra emerges, although Bohr repeatedly said that they come from large quantum numbers. Okay? Here, the claim is that they are coming perhaps from phase transitions and superselection sectors. Okay? This aspect of the problem is not entirely clear. But there is a problem which I can formulate more precisely. So let me consider the bounded operators on a Hilbert space as my algebra of observables. So they are bounded operators on a Hilbert space. And we have argued that one can directly measure only diagonal operators, okay, in this basis. Okay, that they constitute a maximal commuting set. So that only these diagonal operators can be measured. Okay. Now, suppose I know a state on the diagonal algebra. This sentence is not well formed. So what I know is there is some state on the full algebra, and what I know is the value of the state on the diagonal algebra. Okay? So I know rho zero restricted to DH, okay? Where DH are the commutative algebra. Okay? Question: what can we say about the extension of rho zero to all bounded operators? This is what the experimentalist has to do. Okay? That person has to decide from this data what the actual state is on the full algebra. Okay? Can you do it? Well, what are the possible extensions and what is the maximum uncertainty? We can then ask. No, I'll tell you that this is in turn related to another problem. This is related to the problem of Dirac's complete commuting set of operators. Okay? And in 1959, the Cadison and Singer proposed a problem. Okay? It is usually called Cadison-Singer conjecture. Now you can say it as a Cadison-Singer theorem. Okay? Their conjecture was, or problem was, given a pure state on the diagonal operators, so the density matrix restricted to the diagonal operators is rank 1. Does it have a unique extension which is also pure on the full BH? Okay? He said, so there are two issues here. I'm given a pure state on the diagonal algebra, okay, and we want to find its extensions, okay, to bounded operators and show that it is unique and it is pure as well. Okay. For finite dimensional cases, the answer is quite easy to prove. Well, reasonably easy to prove. Okay. However, in the infinite dimensional case, okay, the proof was only accomplished in 2013, okay, by Marcus Spielmann and Srivastava. Okay. And the problem comes here by a rather heavy problem of the fact that there are density matrices, okay, which cannot be written down. In principle, you cannot write them down. They involve axiom of choice. Okay. To construct them involve axiom of choice, but one knows they exist. Okay. So it took all kinds of. It was quite difficult, and the final proof involved something called the Paving Conjecture, and for me it was quite difficult. And this stone check compactification, things of this kind. Okay? But in any case, the final statement is there are finite rank states, okay, or which exist on this algebra, but one cannot in principle write them down. Okay? If you write them down, you would have proved the axiom of choice, okay? For which I don't know, by some other theorem in set theory, probably one can never write it down. Okay? So the problem I am going to state is related to that. Okay? So let me see how it goes. So let me consider the case of the bounded operators, two-dimensional case, okay, which is which people doing quantum information theory, okay, all this qubit business, they are fond of. So the bounded operators are simply two-dimensional matrices, okay, over complex numbers, and the Hilbert space is simply L2 or H2, okay, C2 or whatever it is. And the diagonal operators are the algebra. Diagonal algebra is an algebra like this: A 0 0 B. Okay. Now we are given a state rho 0 on DH. Okay, some state. All that I know is that it looks like this: lambda 1, lambda 2, 0 0 on DH. Okay, and we know that the lambda i's are positive and they sub to 1. Okay. Now, first statement is this rho 0 has a canonical extension to all of M2. That just you use the same matrix on all the 2 by 2 matrices. So you say rho 0 of M is trace of rho 0 M, okay, where M is in M2C. Okay? So this is a canonical extension. It can also be formulated in terms of conditioned expectations, okay, which people doing this paving conjecture, the quantum information people, mathematically inclined people, like to use that, this conditional expectations, but never mind. Okay. This is what it is. Now, suppose that to this rho 0, I can add a sigma. A sigma is a fluctuation, okay, some deviation, and I want to know what I can say about sigma. Okay, it's another. So I want this to be another extension. So, but then since I know the expectation value of the diagonal operators, and they come from row 0, trace of sigma on this diagonal operator is 0. Secondly, rho must be non-negative. So, what can I say about this kind of extension? Okay. Well, if I write the norm of sigma, since sigma is in the space dual to the algebra of observables, it's natural to take this sup norm. So we take trace of sigma A modulus, and I want to find the supremum of this when norm of A, the operator norm of A is 1. Okay. So we want to find the supremum, and also we would like to know where the supremum occurs. Okay. Then take one more supremum, and then because we want to know the maximum error, and supremum norm of sigma, okay, over sigma, we'll call sigma 0, and that is the maximum error we can make. Can I compute it? Well, in the 2 by 2 case, it is quite trivial. Okay? In the 2 by 2 case, one finds that the sigma 0 is given by this non-diagonal matrix, where mod of alpha is the square root of the eigenvalues of lambda 1 and lambda 2, and the norm of sigma 0 is twice square root of lambda 1 and lambda 2. Okay? The proof is, well, I can just give you the proof. Okay? So the first statement is trace of sigma B is 0 for B diagonal. So that says that B sigma has 0 diagonal entries. Okay? And I can write any such sigma as mod alpha times this non-diagonal 0 exponential I theta 0. Okay? Then I look at trace of supremum of sigma A, okay, over all A such that A star A is 1. Okay? So that happens. So the supremum occurs, okay, when this A itself is of this form by Schwarz inequality. Okay? Quite trivial application of Schwarz inequality says this is where the maximum occurs. So you find norm of sigma to be twice mod alpha. Okay? Then you require that the determinant of rho, okay, is non-negative. So rho is of this form. There is an equality sign missing here. Okay? And we want, so the maximum uncertainty, maximum value of mod sigma occurs at the boundary. Okay, so that happens when determinant of rho is 0. So that happens. So you find immediately that mod alpha is lambda 1, lambda 2, and sigma 0 is exactly this. And norm of sigma 0 is twice square root of lambda 1, lambda 2. Now, the point I want to make is that even in this 2 by 2 case, the extension is not unique. Okay? You give me the diagonal state. If it were a pure state you started from, then lambda 2 is 0, then sigma 0 is simply 0. Okay? That is the statement of the Catastrophic single theorem, okay? In the 2-dimensional case. Okay? But if lambda 2 is not, lambda 1 and lambda 2 are not 0, okay, then you see that sigma 0 is not unique. The maximum uncertainty you can find is not unique. There is this phase. The phase cannot be determined by this. The extension will, even for the maximum error, there is a problem in finding the error. Okay? So the expectation value of observables cannot be determined because of the angle, even in the 2 by 2 case. Okay? So, but we can also note that the phase comes from the stability group. Okay? Rho 0 is a diagonal operator. So if I rotate around it, okay, exponential I sigma 3 theta over 2, and I conjugate this whole expression, then you find that this conjugation does not change rho 0, and there is a mod alpha missing. You find this expression for the second term. So there should have been a mod alpha here. Okay. Okay. So this is coming purely from the stability group of the diagonal operators. Okay. Now we can say inquire what happens in higher dimensions. Okay. One finds that the boundary, I mean, you would expect that the error is maximized at the boundary of determinant of rho being non-negative is set with the boundary where the boundary being determinant rho is equal to 0. Okay, and we find that in the higher dimension, higher than 2, that area, that surface is stratified with the rank of rho. Okay? So suppose you take a 3 by 3 matrix, I'll simply state the results. Okay? And I ask, give me any 3 by 3 matrix, lambda 1, lambda 2, lambda 3 are all non-zero, and they sum to 1 and they are all non-negative. Okay? And I ask, find the extension so that rho 0 is of rank 3 or less. Okay? It turns out that all these, there is a choice of sigma where all of them are realized. Okay? For example, if I say is of rank 1, all that happens is that, so there is I will find a class of sigmas where this extension is of rank 1. So it will occur if alpha bar is equal to lambda 1, lambda 2, beta bar is lambda 1, lambda 3, gamma bar is lambda 2, lambda 3, but their phases are undetermined. You can find this result by simple applications of moment problem. Okay? Non-negativity of matrices. Okay? So the determinant of sigma in this case, okay, is bounded. I should not say equal to. Determinant of sigma is bounded between a maximum and a minimum, which happens to be the product of all these things, okay, square rooted. Okay? So with a 2 in front. 2 in front, when you do the calculation, you get a 2. Okay? So it's a product of all these operators, which is square rooted, you get this expression. Okay? Rank 2, you get another set of possibilities where alpha bar is fixed like this, but the other ones are in open regions. Okay? So they are less than this. So you get inequalities. There is an open set. Okay, and for the last 2 variables, and still you are in the boundary where determinant of rank rho is 0. It's a rank 2 in the 3 by 3 case. So you find determinant of sigma lies between 2 extremes. If you compute it, okay. We did not compute the norm because it looks messy. Okay? There are some cubic equations you get, which one does I don't want to solve. Okay, so it seems that determinant is much easier to handle. Okay? So this goes on for n dimensions. Give me the rank n density matrix on the diagonal operators. Okay, then so it is some rho 0 where all the entries along the diagonal are non-zero, and I ask, find an extension which is of any rank less than n. Okay? I can find a extra term sigma, okay, so that rank is realized, okay, without disturbing the given value on the diagonal operators. So it is highly uncertain. Okay? How can we resolve this issue? Okay? Because this is assuming that we can only measure diagonal operators directly, that the knowledge of what the density matrix takes on the remaining operators is quite uncertain. How do we resolve it? I will come back to this in a minute. Okay? This has consequences. Okay? Well, the first consequence is that this will, I don't know how it is resolved. Let me say, if suppose somebody wants to measure, prepare a state, for example, an entangled. So the rank 1 cases, which I have talked about by adding sigma, are maximally entangled between all the sides. That is, all the, if you think of the n by n matrices, n sides, the pure state that you get is maximally entangled between them, but there are phase uncertainties with which you can change it. Okay? So in the vector state, you can change some relative phases, and that is where, by operating with the stability group of this rho 0. Okay? So rank 2, the entanglement is 1 less, and so forth. It goes like that. So they're all entangled states. I suppose you should want to prepare them. How would one do that? Okay? The experimentalist only measures apparently only diagonal observables. Then how does one know what has been created is entangled, or what is it? Okay? In the full algebra of observables, it is not clear, but I'll come back to this issue in a minute. there is also a curious uncertainty principle. The rotation or the stability group does not commute with the sigma. Okay? These are operators we acting on a Hilbert space. Okay? For example, the sigma is a 3x3 matrix acting on H three-dimensional Hilbert space. Okay? And the operator which rotates them, which is a stability group of rho 0, is an operator on this, can be regarded as an operator on this Hilbert space. They are somehow conjugate variables, like momentum and position. Okay? Not exactly, more like angular momentum components. If that is the case, there will be some kind of uncertainty principle governing this angle and or these elements of U1, elements of the Cartan subalgebra of the SUN group, which is here, okay, and the sigma, which will say that if you know sigma exactly, you can never determine this angle. Okay? I don't know what it means, okay? But underlying this is that fact. Okay? So I just want to make sure that to communicate this, but I think that this line of argument has impact on preparation of states and undoubtedly in other contexts. Okay? So I can say here, one possibility, which we got this idea yesterday by discussing, okay, is that by this uncertainty can be reduced, okay, by there is this business called radon transform, which you may know, okay, which is used in things like CAT scan, where you take X-rays or the slices of, say, your brain or whatever it is, then you try to reconstruct the full three-dimensional picture. Okay? Likewise, here one can imagine measuring several diagonal operators. The maximal commuting set is not unique. You can conjugate it by a unitary. You get another maximal commuting set. So I can ask, if I give data on all the maximal or enough maximal commuting sets, can I recover the full state uniquely? Okay? I suspect, but I am not sure, that one can reduce these uncertainties I am bringing to your attention greatly. Okay? So this is something we are in the process of investigation. I think there is an answer. So we will come back to this. Okay? We will have something to say. Okay? Now, this whole thing suggests a problem. Okay? Suppose I am given a KMS state on an abelian algebra generated by a complete community set. Okay? It could be operators which are associated with chemical potential or other appropriate conservation laws. And I'm given a complete community. I give you what the KMS state does or the thermal state does on the complete community set. Okay? What is the extension to the full algebra of observables? How far can I reconstruct the KMS state, okay, in its detail? Okay? The KMS Hamiltonian or whatever other data I may require to write down the state. How far can I go given this information on the expectation values of a complete community set? Okay? Yeah. I don't know. Okay? This is related again to this problem of Caddis and Singer, okay? And I don't know the answer. Okay? Now, there is a conjecture, okay? Natural conjecture which comes from here. Okay? It may be, well, it is the fact that thermodynamics is now disjoined from the rest of physics. You don't know. I mean, it seems to be a closed system. Okay, what is it? Okay? How is it related? In what way can I bring it closer to what we do in local quantum physics? So there is a conjecture which I doubt is new, okay, that the thermodynamic variables, for example, deduced from a partition function, are labels of supersolution sectors. Okay? I don't know whether this is correct, but it should be possible to check them in some models. Okay? And they will be some classical, they are classical variables and they generate classical algebras. So there is some possibility that this connection exists. Okay? I said, I don't think this conjecture or this guess is new. Okay? And if you read these papers of Fiorini and Giorgio, okay, 1994, or Arthur Weidman's lecture, I think it was a presentation in some meeting, okay, one would see statements or arguments which are very close to what I am saying here. So that should be, so I don't think that what I am saying is new. Okay. So let me now go back here. Okay. So I thank you and I finished. Thanks. I'm finished. Hello.
Thanks, Bal. Thanks for an excellent presentation of a large set of ideas. And the floor is open to questions. Bernard.
Well, of course, the problem would not arrive at all if one does not ask for something like a Copenhagen interpretation. And I just what I don't understand is a good characterization. If one wants to have something like Copenhagen interpretation, what are the possible measurements at all possible? And there is your approach, and presumably there something similar from the experimental side, because the whole thing got additional interest with the Bell inequality and so on, the aspect measurement. Is there anything related to quantum field theory?
Well, as the statements I'm making, well, the statement, Weidmann's interpretation, also Giorgio and Fiorini, okay, is that these superselection operators are in fact the observables which our masters and mistresses were talking at that time, okay, that Bohr was talking about. Okay?
Yeah.
They kept talking about large systems, okay, or large quantum numbers. Okay? And if one checks, this is all I know, I'm telling what I know. If one checks typical superselection systems in quantum field theory, for example, in quantum electrodynamics, okay, these superselection, for example, in quantum electrodynamics, the infrared problem leads to a whole class of superselection sectors. Okay? They're labeled by some test function which is not compactly supported. It goes to infinity. Okay? And its asymptotic behavior labels the superselection sectors. Okay? For example, or in some other problem where, for example, if you have a non-abelian QCD, okay, the Cartan-Sub algebra of the non-abelian QCD will give a complete commuting set of operators, and they can take a sequence of values. So they will generate some algebra, and that will be, since Cartan-Sub algebra, it is a commutative algebra. So they all come from infinity. The charge selection rule comes from E dot ds at infinity, which can be written in terms of local operators, but the original argument regarding that was that it is superselection because it is an operator at infinity. So I think that the claim here is that the quantum field theory provides you enough operators of this sort, okay, for the actual measurement. Now, one has to know what is it that is. The problem here is not that whether you can measure it or not, because all the time measurements are going on. The problem is to understand what is it that is being measured. Okay? It seems that and we have to agree that everything is quantum. So if you have a classical algebra within a quantum system, the whatever you do will be classical on that. Okay? You will have the Kolmogorov axioms, everything will be there. Okay? The pure states are all delta functions of various kinds. Okay? So they will all be there. So the conjecture is that A, quantum field theory provides enough supercelestial sectors, maybe through phase transitions of the apparatus, and B, what we are measuring is these operators. What the experimentalist is actually doing is measuring these operators. Okay? The second part is much more difficult for me to handle. One has to know much more deeply the experimental setup. Okay? The first may be correct. I don't know. So this is let's say this is the status of the problem. I don't know whether I answered you.
Yeah. Well, I was thinking about relation to work by Ian Job and Milan, and so late last year when they tried to work on contradiction between measurement theory and causality, but I didn't read it in enough detail. Did you happen to look at that? Or?
I did. At that time, I was communicating with both Ian and Leron,
Yeah.
and also looked at phase papers. But once I got convinced that the standard measurement theory is not appropriate in quantum field theory,
Yeah.
but more something along the lines of what comes in the formulation of Bogoliubov, where he. Then I did not pursue it any longer.
Yeah. Okay. Yeah. Thank you.
Some other questions? Does somebody want to ask a question? Or let me, Val, just I am reminded a little bit of the interpretation that Jörg Frohlich was putting on this. He insists as well that you need these local observables, if I understood him correctly. I think you're familiar with his lectures on that. Do you want to comment? Can you comment on that interpretation, or perhaps someone else? Arthur, he gave a lecture in your series on that.
Let me say that I tried to understand Jörg Frohlich, and I failed. Maybe one of you can explain to me what it is. I could not follow his papers. Okay?
I think after he gave a lecture here in Dias, right, or at least on Zoom.
Yeah.
Right.
Yeah, it was a joint lecture with Arthur and that.
I remember looking into the stuff afterwards, and the way in which everything is formulated, it skirts around the issue of when you'd have the kind of trio of observables that Val introduced at the beginning, Raphael's picture, where you can have observables not entirely to the future of each other, where the future of one observable kind of cuts another one. So part of a second observable is in the future of the first, but part of it is not. And if you don't consider those kind of situations, then you don't have any problems with the standard measurement theory of quantum mechanics being directly applied to quantum field theory. This was something that Raphael pointed out in his original paper, actually. So yeah, I didn't think that the issue was touched on so much there.
Thanks, Ian.
What I know is that Giorgio is here, I think. For reasons I do not know.
Yes, of course, I'm here.
Giorgio is here. Apparently, Jörg Frohlich dismisses Hep, saying that he has done nothing. But when I read Hep, it's extremely interesting. He makes explicit models. For example, how a photographic plate works using silver bromide, which acts as a catalyst, the catastrophic transition of the whole system. So, I personally liked it paper very much. But Giorgio says Hep dismisses it. I don't. Okay, so there's some conflict. Hep was Frohlich was a student of Hep, So I don't know what the conflict is.
Okay, that's Jörg isn't here to answer. So
Giorgio is here. He can tell something.
I thought that Hepp's work was very good. I mean, his point was defining what's macroscopic. I think that was his point essentially, which is of course the interesting point. You see, and showing that macroscopic observables commute and behave as what you expect, namely what classical commute and that two macroscopic objects cannot be observed simultaneously. You know, I'm thinking of the cat, of course. I'm thinking of the Schrödinger cat that cannot be seen as being dead or alive because the two states are disconnected. They're not. There is no operator which can allow you to see the cat dead and alive at the same time. You don't see states. You see operators, of course. You see observables, and there is what Hepp proved was that there were no observables which mediate between the two states, which are disconnected.
I mean, that is also what Weitman, if you are super selected, the observables, I mean, the experimentalist is
of course.
accepting only.
Quite right. Yes, I saw Weitman papers because Sachin sent it to me very kindly.
Yeah,
I didn't know it.
I know. I mean, he sent it to all of us. I didn't know this paper. It rather explicitly says the kind of things that I'm saying. Okay. So this, in some way or other, this knowledge has been there for a long time. Of course, if it is a commutative algebra that one is observing, then none of these strange paradoxes appear. Okay? So it seems to me that the only issue is that if you write a local coupling, for example, disturbing the system being observed, okay, how does it affect the actual measurement of an appropriate commutative algebra? Can one make a detailed model of how this happens? Okay? How does, for example, for example, in the Hepp case, okay, there are two possibilities where the silver bromide atom flips its spin or does not, and the result is quite different for the global system. Okay, so there must be such possibilities, but can we model it better? Okay, I don't know. At least we have not found an appropriate model. Okay? We are trying to think about it, but we don't know it. Okay? But personally, I am also struck by the fact that the measurement of a complete community set, okay, will tell you there's a lot of error in telling what that algebra is on the full system. Okay, this cannot be what the experimentalist is doing. Okay? I suspect that this is because the experimentalist is taking these different cuts of the complete community sets, okay, and requiring the state to behave appropriately in each of them. Then there's some reconstruction. This is my suspicion.
That seems correct, Val, because the experimental doesn't just take one observation. They wait some time, they come back, and the apparatus would have changed. It would have evolved.
Yeah. So
I think Arthur has unmuted, so I think he may have a question or something or a comment.
Okay.
I don't have a question, but I have a couple of observations about this really interesting talk. I don't know if they're relevant observations, but just make them. First, the first part of your talk reminded me very much of the proof of the Race-Leader theorem, and I wondered if this is some superversion of that theorem.
Yes, it is just like, if you like, it's a footnote to the Race-Leader theorem.
Yeah, and the second observation is that if you think of measurement by diagonalizing coordinates, and then you have the conjugate momenta variables, and you have the standard uncertainty principle, which we know is maximized by Gaussians. There are many uncertainty principles involving entropy that are maximized by Gaussians for classical, I call that the classical system. And then there's an extension of that where you define the Fourier transform in a more general way on operators, not the standard Fourier transform, but some other type of Fourier transform. And this gives rise to a new type of uncertainty principle, which we call quantum Fourier analysis, and it involves the Neumann entropy instead of the standard entropy. And I just wondered if this, it's maximized not by Gaussian functions, but by biprojections. And biprojections are projections whose Fourier transform in this unusual sense are multiples of projections. And this could be related to this theory of measurement.
I mean, so I don't know this, what you call quantum Fourier transforms. You suggest that there may be some insight into what is happening in that context. That's what, if I understand correctly.
Well, I'm not sure this is actually connected, but I thought that this must be.
Okay.
And it's a subject of open subject for research because these ideas are not completely worked out.
Okay. I was thinking more along the radon transform. Okay. I mean, I want to know how accurately I can determine the state. Okay. What kind of measurements I have to do, given assuming that I only measure commuting operators. Okay. Then it looks very similar to the problem of the radon transform, okay, where you construct the whole function by taking Fourier transforms on planes in various directions.
But I'm just saying that, yes, this is very interesting, but I'm just saying that there's this quantum version of the uncertainty principle, which looks like it could be connected to the Catastrophic problem.
Okay.
And then it should be related to this measurement that you've been talking about too. Okay. Maybe the radon transform is another way to think about that. I'm not sure, but there are examples in which this quantum Fourier transform has been worked out, especially in papers of Chang, Liu, Wu, where they show that these biprojections maximize the inequalities. And that's a fantastic thing because this was a very deep result of Beckner, Lee, Bracekamp, Tao, many other people about showing that classical Fourier inequalities are almost always seem to be maximized by Gaussian functions. That's very strange. And then there's a quantum analog of that.
Okay, thanks. I will look it up.
Can you give us the most accessible reference to that?
Well, this is.
I know you're a long review on it.
At the end point, I mean, earlier last year, I was a co-author of a paper. I can put the reference in the chat, but this goes back 4 or 5 years to this. There's a set of about 10 papers, and maybe I send it to you.
No, I'm broadly familiar with it because I've seen Cheng Wei's lecture and
yeah, so Cheng Wei was one of the first persons, if not the first one, to introduce these ideas.
Just to highlight the simplest example that you did where the entropy is maximized by projections, that's just that aspect alone to pick it out, yeah, where would that be most accessible?
I think that's in a paper of the 3 authors in Journal of Functional Analysis around 2016.
Yeah, that would be the one that would be most useful, I believe. That's excellent. Thank you. Other comments or questions? If there aren't, I will stop the recording and we can chat less formally.
Okay.
Okay.